is like we did, what was that, last week, okay? Expressing with a common base. So that you do not need logs. You can't show with a base of 4, but you can show both of them with a base of 2. Okay, so take a look at the difference between that question and question 2. So kind of similar in the fact that it's just a constant on one side and a power on the other side with x in the exponent. But the bases have nothing in common with each other. They're both prime numbers even. So there's no way I can express 7 with a base of 3 or vice versa. So it can't be solved because there is no way to express 7 with 7 as a power. Okay, so it says solve it algebraically. Well, what do we know? We now know that a logarithm is the value of the exponent. So taking a look at this, I can then think, okay, that base of that exponent can be the base of my logarithm. This is the value of my log, of the exponent, which is going to be the value of the log. And so the argument is 3, right? So 3, if you think about working backwards to check my swoop, so you can put brackets there if you need to. 7 to the exponent x plus 4 has to equal 3. Okay? So the base there is the base here. So now to get x by itself, there you go. Okay? So that's using the definition of the logarithm, converting it from exponential form to logarithmic form. If there's a variable in more than one exponent, then we're going to do something a little bit different. We can't just convert it right away, because if we did, we basically have here 3 to the x there, and we then have x's on both sides. It would be much more complicated. But if there's just one power with an exponent, the variable in that exponent, then you can just convert it into logarithmic form. Guys, are you good back there? Okay. So let's do that. And the next one says, solve algebraically, express each answer as an exact value, and as well find the decimal form. Take a look. This, I can't express 2 or 5 with the same base. Always check, because that's really fast, right? If you can't. You can't. Take a look. There's a variable in both exponents. So to convert that into logarithmic form, you have exponent with x in it in a couple of different places. So think about back to junior high or even before, when you started solving equations. Whatever you do to one side, you do to the other. So if I have 2x equals 16, if I want to solve for x, I divide both sides by 2. Well, here, if I if I treat both sides the same, what I can do is take the log of both sides. Okay, I've treated both the same. If you do it to one side, just remember you have to do it to the entire side. So sometimes it may or may not help you, but we're taking the log of both sides. And what's great about this is the power law. Power law says that we can show this exponent of 3x as a coefficient. Okay, now the variable is not in the exponent. Right side, okay, now my exponents, and now I don't have exponents anymore. Okay, so basically I'm converting the left side into a logarithm and the right side into a logarithm. Now, there's x's on both sides, so we have to collect them. We can't just divide by log 5 though, because we still have x's, right? So just like you did with trig or with any more complicated, you want to get rid of the brackets. So expand. Remember, these are just numbers now. This is just a number. Right? You could evaluate it. You have the decimal form. But this is really just like x minus 1 times some number. That's 3x times some number. Okay? It's just, because it's bigger, we put it after the variable there. You could put 3 log 2 in brackets times x. But that's usually how we show it. Now, I want to get the x terms together. Okay. Notice how this does not become 2x log negative 3. Right? This is a number. You cannot subtract the arguments. You only subtract if it was a division statement. So I show this as 2 separate statements. This is a number, this is a number, right? They're not the same value. So now I'm going to factor out whatever is common, the x. I need to isolate x, and there's x in 2 terms there. So now to get x by itself, we need to divide by that bracket. And that's your exact value.
If you want to read it, so for example, instead of 3 log 2, you can read it log 8.
You could, yep. So we'll accept this, okay? You could show it in a few different ways. And this is what I said on a diploma exam. Maybe, or a cumulative or whatever, there's a multiple choice. You might say, which of the following is not a solution? Because I could show it this way. I could show it as log of 8 minus log of 5 in the denominator. I could also show it as log of 1/5 over log of 8/5. Okay? That's subtracting there, so I can divide the arguments. I could also...
you could factor a negative in the bottom, cancel with negative, that's nice.
Yeah, you could. You could also, this could be change of base, right? We could change this to that into 8/5, 1/5. So there's few different ways, right? You could factor, that could go down below.
It's the nice thing about logs, you just want to express it a bunch of
So
different
down there, it would be negative log 8 plus log 5, so that would be log of 5 over 8. And then you can do the same thing there. So many choices. But the first one is fine.
I like to after one.
Yeah, they will be on the other side. So don't do it.
Well, that's the they can't really mark it wrong, can they?
You might, it's not right in the Okay. So I did say to find the value of it. Do you even have to enter that into your calculator like that to get the value? What's one way to do it without just entering the values in? If we're solving an equation, you could graph it. So for those of you, well, actually, this has log base 10, so it's okay. If it was a different log base, like if you showed it with a different log base there, you'd have to use change of base if you don't have a calculator, right, with that capability. So you could graph it. Okay, so here, you want to use fraction form, so to make sure that you don't because here, if you don't use fraction form, you have to have brackets around that denominator. And if you don't, you're in trouble. But if you do use the fraction capability, then you don't have to have brackets around the whole thing. Okay, so negative 3.42. Did we say what's around 2? Here's 10th, so negative 3.4. Okay, so this is how you can get exact values, which is as solutions for any exponential equation. So it's really important stuff as you move forward. Okay, now. So we can't show the 6 with the base of 3. Please don't do this. I will have to get my hair dyed again. Okay? Do not do that. What did I do there?
It's not the same base. You multiplied the bases.
I multiplied the bases. Can I do that? No, they're not the same base. Can't multiply them with, there's an exponent on that, right? So please do not do that. I've seen grade 12 students do that, and it, not good. So, take the log of both sides. Okay, if you want to put that in big brackets, you can. Okay, another common error, be careful on the right-hand side. Guys, are you doing this? Did you put a pencil in your hand rather than a hole puncher? Okay, so that's going to go in front. Now, here, can I do this? No. Remember that was the last one on that true and false chart yesterday. This only refers to the 6. I cannot do that. Do not copy out what I have there. I need to use the product law. This is a product of 2 and 6 to the x minus 1. So this is going to be log of 2 plus log of 6 to the x minus 1. You don't want to go right away to the parallel rule. You can do that in the same step, rather than taking 2 steps to get there. And another thing is if you show me this, it's wrong. actually wrong, because that's saying plus x minus 1 times log 6. We need the brackets around that. Okay. So even though there aren't brackets around the exponent to start, if it's more than one term, you need brackets. If it's just one term, then that's just straight multiplying, so you're good. Now, x is on both sides, so I'm going to expand those brackets. And now get the x terms on one side, just as we did back in junior high, right? It's no different. It's just that the number's a little bit different. Like if log 3 is just a number, but you have a word with it, right? So it's different meaning. It's still just a number. Okay, and factor out the x. And I leave them as separate terms. Yes, this is a subtraction, so you could show that as 2 over 6, which is 1/3. I kind of wait till the end, just to see what ends up happening, but you could change that right now if you wanted to. Again, we're going to accept this. Okay, so that I will accept. But if it's in a multiple choice and you don't see it there, maybe it's been simplified in a different way, right? Maybe it's been, in this case, we've shown this as log of 2 over 6, which is 1/3. This would be log of 9, so that would be log 9 minus log 6. 9 over 6 is 3 over 2. Sometimes we don't like having fractions in the argument, so that's why we keep it as the original. Saying that, we can check, like, if we simplify it, do it both ways and make sure you get the same thing. So if I go alpha y equals, so here, I go log 2 minus log 6 to log 3 minus log 6. Okay, then I do log of 1 divided by, let's do it in fraction form. Log of 1 divided by 3. Log of 3 divided by 2. And I get the same thing. Okay, but this is not equal to log of 2/9. Okay, so if you see logs with the same base, you do not divide the arguments. You divide them when you're subtracting logs with the same base. You can use the change of base formula. So you could show this. So this was or log. This argument here becomes your base. So you could show it like that. You could check it on most of your calculators. You have that capability. Sorry, so now 3 divided 2, 1 divided 3. Okay, back to the same.
I think it looks nicer when it's all nice and simplified into one longer.
Yeah, it does. but it also has fractions. So. Okay, so those are exponential equations that we're using logs to solve. Now take a look at log equations. So in log equations, what are you logging? Yes,
I think the value of
try to say it louder.
values, we need to put the log between the and.
Oh, right, I didn't write it down, did I? Okay. All right, so log equations. We've really kind of already done some of these. The ones that we haven't done are maybe more like C and on the next page. But this is just a single log equal to a constant. Do your swoop, and convert it to exponential form. So if there's just one log, you can convert it right away to exponential form. So that says 9 to the 1/2 equals x plus 1. And solve for this. It does remind you to check for extraneous roots. Okay. So remember here, we know that x has to be greater than -1. So just make sure your solution that you get is greater than -1. 9 to the 1/2 is 3. X is 2.
Because the other solution you get would be -4. That doesn't work.
Here, in this one? Plus minus? Oh, I see. So yeah, because we're raising it to the 1/2. So yeah, I guess I should put that plus or minus because we're taking the square root. So then our possible solutions, yeah, that's true. So possible solutions would be 2 and -4, but then we eliminate that because it is an extraneous solution. Yeah, good point. In the real world, yeah. Okay, next one. X squared equals 16. So now we're taking the square root, so tend not to forget about it when it's in this form, right? So we know plus or minus 4 there. We know by definition that x has to be greater than 0. So we just rewrite 4 is our solution. Next one now has more than one term with x in it, maybe some more than one log term. In this case, it's log base 3 equals log base 3. So that is kind of like exponent of 4, sorry, base of 4 equals a base of 4. The exponents have to be equal. Here, this argument has to be equal to this one. So we can go straight away to this, because this is the same as this. Both are log base 3. There are different log bases, then you couldn't do that. Now that's a quadratic. And you can solve that one by factoring. Okay. equation defined for. So for this, x has to be greater than 0. So right away, we know that it's not going to be negative 2. Okay? This, x squared, I'm just going to do it down here because I'm too short to fit it in up there. X squared minus 8 has to be greater than 0. So think about that on a number line. What makes this equal to 0? What value of x would be the positive root 8 or negative root 8, which is 2 root 2. So when is it positive? For these values and these values, right? For x. So that, and we'll do it in green. So that's for this is x less than 2 root 2, x greater than 2 root 2. Remember, overall, what overlaps, right? So x greater than 0, 0 would be in here, right? And so this part is what overlaps for x greater than 2 root 2. So that doesn't even come into play, right? We can't have an x value of 0. If we put it back in the original, it would make that left-hand side undefined. So x has to be greater than 2 root 2. Is 4 bigger than 2 root 2? Yep. So that's our solution. Okay.
Sorry, for the previous question, why was x greater than 2?
Try and take
For the definition of a log, the base has to be greater than 0.
Oh.
And not equal to 1.
Oh, once you get to the complex world logic, there's like so much more you can do. So nice.
Okay, D. So you could rearrange to get the x term by itself. You can leave it like that. You're subtracting logs with the same base, so you could divide the arguments. If you wanted to isolate the term with x in it right away, you could. And then you're adding logs with the same base, so you multiply the arguments. The same log base on both sides, and the arguments have to be equal. And that satisfies here, x has to be greater than 0, which this is. Okay, next one. Two terms with x in them. Okay, so they're both on the same side. I'll keep them there. Coefficients are 1, same base, and so it's addition, so that means we can show it as a product. Okay, now be careful. Some students will tell me this. Okay? So they will see that and they'll think kind of like the last one, where the argument here is equal, needs to be to the argument of a log, but this is not a log. So I would convert this to logarithmic form by doing my little. So 2 cubed is x times x plus 4. and then expand. It's a quadratic, so get all the terms on one side. You can't factor, then use the quadratic formula.
Oh, wait, no.
Okay, so gotta look back, not at the combined form here. So don't even worry about this. You go back to the original form. X has to be greater than 0. X has to be greater than -4. Where's the winner on that? That is this. So we need to choose the X value that is positive. So just make sure that you get one that's positive. Negative, remember 2 root 3 is going to be bigger than 2. So if I start with -2 and add 2 root 3, I'll get a positive. If I subtract, obviously it's going to be negative. So my solution is going to be the plus 2 root 3. X, 2 terms with X in it, 1 on each side. You might want to bring 1 term over. If you do, you'll be subtracting, and then that means it's going to be a division, it'll be a rational expression in there. So, which is fine. I might actually leave it as is, because adding means you're taking a product, which is pretty easy to do, right? And now we've got log on each side with the same base. So that means each argument has to be equal. And then it's just a linear equation to solve. Then check. So here, X has to be greater than 1/3. x has to be greater than 1. So where is the overlap? It's there. And this is 2. So that's greater than 1. Obviously, you could also go back and substitute it in the check. Okay, so G, we've got two terms with x's in them, both log terms, both base 2. But we also have a constant term. So you could, one thing is you could express log, and you could express 2 as a log with base 2, if you wanted to. Or I would probably, right now, just collect the terms that have x in it, right? So this would be log of x base 2 minus 1/2 log of x minus 3 base 2 equals 2. Okay? I have a coefficient, it's a half. Which means really I can show that as square root of x minus 3. Okay? It's kind of annoying. Think about whatever you do to one side, you do it to the other, you're not changing the equation. So remember back to rationals, right? We looked and found the common denominator and multiplied both sides. So I might multiply both sides by 2.
To get rid of the 1/2.
Yep. So now I'm subtracting logs. Careful though, I still have a coefficient. So I had a coefficient there, so I would have to use the power law. Now I still have a coefficient. It's just nicer. 2 is nicer than a half. So now I can show this as x squared. And now I can show that as a single log of x squared over x minus 3. And then I can convert that to exponential form. You can think about it. Even if you left it as 1/2, you'd show that x minus 3 is square root. You're obviously going to have to square at some point. And so now we've done that. Is 16. So this is going to be 16 times x minus 3 equals x squared. Multiply both sides by x minus 3. And it's quadratic. So get everything on one side. After that, yes. Okay, so now, going back to the beginning, where is it? Way up there. So x has to be greater than 0, x has to be greater than 3. So this is the overlap. Notice how, listening folks, notice how at some point I'm showing this as a rational, so I can't have 0 down here. But will this ever be 0? That's greater than 3, not greater than or equal to 3. So it's not really going to become an issue, right? Because that was from an argument of one term above, and it can't be equal to 0 anyway. So greater than 3, both of these are greater than 3. So Newton.
So would there ever be like an example where we would have to look like in our steps to find any restrictions? Or would we always just be able to look at the original function?
I think always going back to the original is going to work for at this level. I'm trying to think if that was quadratic in there. It's still going to be greater than 0. Yeah, I think you're still good. Okay, so think carefully about the next one. It's kind of the same. 2 terms have x in it, and 1 term is a constant term. Oh, where is it? 8. Oh, it's there. I wrote it way too big. So let's do hold on. No, that's really big. Okay, so it'll be up to you. You could convert 1 to a log with base 9 if you wanted to. Okay, so maybe, why don't we do that? Because it's a little bit different method rather than bringing the x terms together. Just in case you might prefer that.
Well, I kind of saw why I put that. Oh wait, no, not that one. Never mind, not that one.
So 1 is the same, remember, if we have base 9, as log of 9, base 9. Argument and base are the same, gives you a value of 1. So now, using the power law, 2 is the exponent, adding logs with the same base. You can multiply the arguments. And so now we've got an equation where the arguments of each log are equal. So this is a slightly different way, but you'll end up with the same quadratic that you have to solve. So I express this as a logarithm. Then adding logs with the same base, I multiply the arguments. Here I use the power law. So therefore, x minus 3 squared is equal to 9 times x plus 1. Expand it out, plot like terms, solve for x. might think, oh, yeah, x can't be 0. Well, it depends where x is. That's only if you're taking log of x that it can't be 0. So looking up here, I know x has to be greater than 3. X has to be greater than -1. Both of those are. Oh, sorry. Sorry.
Just put on the math.
Sorry. Where do they overlap? It's got to be greater than 3. So this one, so we cross out 0. Sorry. My little brain is there. Okay, and last one is I. Take a look closely at it. There are brackets around the log x. So it's not the power rule for our logs.
This is log x squared is log x plus log x. This is log x times log x.
Okay, so just also be aware, remember how sine of x squared, we really usually show it like that, sine squared of x, that means this. There is no such thing as this.
I've seen that.
Not normal. Maybe somewhere I'm not seeing it, but maybe there is, but we do not use that. So we use brackets. Squared, it's squared. Okay, there's no law for that. It means log of x times log of x. And there's no special rule for that. This, however, is x to the -1. So that's not inverse of x. That's x raised to the exponent -1. So that is, I'm just going to copy that out. So it's 1 over x, or what's nicer, because I don't like having fractions in my arguments, it's the same as -1. So I'll just show it as minus log x. Now I have, hey folks, I have a squared term. I have a term that's just to the exponent 1 per se, log of x, and a constant term. So just like we did for trig, maybe, and you don't have to show the substitution if you can factor it right away, but maybe what you're doing is let a equal log of x. So this would really be a squared minus a. Bring that over, minus 12 equals 0. And then you can factor it out. With trig, we did it with exponentials as well. So -12, two numbers are multiplied to -12, out to -1 are -4 and +3. And so if I put my log of x back in, that's my equation. That's the factor form of my equation. Then I solve each factor. It's not x plus 3 in brackets, it's log of x plus 3. So this will be log of x equals 4. Log of x equals -3. Log is base 10. to the fourth equals x, so x equals 10 to the fourth, which is 10,000. 10 to the negative 3 is x, so x equals 10 to the negative 3, which is 1 over 1,000. And back up here, x has to be greater than 0. So x has to be greater than 0, which both of these are. Okay, so that is a very good sampling of a variety of exponential equations and log equations. This week, please, for a couple more minutes. Next week, we get into applications, both exponential and logs, and we need to use logs probably in both of them if we're going to look for exact values. So that's Monday,